we're talking about this question of plateau. So let me just restate that. I was a little imprecise what exactly we're doing. Right, so we have this plateaus problem. Right, so the idea is, let's suppose we have C inside of, well, let's just simplify and assume we're just in Euclidean space and not have this issue with the manifold. So let's say this is a simple closed curve. And let's just assume it's a simple closed smooth curve. So this part you can certainly relax, but for simplicity, let's suppose it's a simple closed smooth curve. So the problem that sort of that's plateau's problem again has the following sort of question is, can we fill in this curve C to a area minimizing disk, right? So this is this existence part of the question. So what this means precisely is, does there exist a gamma that takes the closed unit disk to Rn with which is, say, with in some regularity class, which we won't specify, but let's say maybe just assume it's in a class where the area makes sense. So, but it's even interesting if we just assume it's smooth. So smooth as a map, and so that if you look at the restriction of gamma to the boundary of the disk, which we call little gamma, that this takes the boundary of the disk to C is nice. Okay, so in other words, we want to kind of fill in the curve C with the disk, and we do it by picking some parameterization of the boundary and then filling in that parameterization. But notice, and this is the part where I was a little imprecise last time. I mean, we're not telling you the parameterization of the boundary beforehand, and that's sort of important. So then the other part is the sort of regularity, right? So I mean, in principle, even if this is a smooth map, I mean, somehow it could be fairly irregular in the sense that I mean, the image. I mean, there could be lots and lots of branching behavior. So the irregularity, in a sense, is can we take gamma to be a conformal or a weakly conformal? So we have to allow branching, as we saw in higher codimension, or dimension n bigger than or equal to 2, a weakly conformal harmonic map. Right, so this is, in general, the best regularity we could expect. And then this question that I sort of called like stronger regularity, but maybe we should call it the regularity of the image. Okay, so when can we say when is the image, when is say gamma sort of an immersion? So when is the image really a nice? I mean, when do we not have sort of potential branching or sort of bad problems in the image, sort of singular behavior, and then even better, like when is the image, you know, say smooth? So by the image being smooth, I just mean it can be locally straightened by sort of local diffeomorphisms. So the idea is, right, even if you have an immersion, if you're not in an injective map, then the image would not be smooth in our sense. So this is really asking when can you take gamma to be, say, an injection? Okay, so let's call these like 1. Right, so of course, as I said, sort of a gamma that satisfies 1 and 2 is called say a plateau solution. Right, and so then the theorem, as I said, which I'll give a kind of outline of the argument, this is due to Jesse Douglas, as I said, and Rado independently about the same time, and then Mori extended it to when you were into a manifold rather than Euclidean space, so that they're given. Okay, this is given, and this is the point. Is this is area minimizing. So by area minimizing, one has to be a little precise here. So area minimizing means where you compare with other possible disk emerge type solutions. So other guys gamma of this form. So you could always, in general, you could try and compare with where you change the topology but fix the boundary curve. But that goes to a different type of problem. Okay, so given such a C, there exists a plateau solution. Okay, so in other words, for any simple closed curve in any Euclidean space, you can always fill it in with an area minimizing disk. Of course, as we saw, we know that that disk is in some parameterization going to be weakly conformal and a harmonic map. But as we saw, to drop that weakly part to make it really conformal in an immersion, we can't do when n is equal to 2. So then it can be done in a slightly. So this is due to Osserman and Gulliver, which I probably should really reverse their names to be consistent. So the plateau, so if n equal 3, then the plateau solution has no interior branch points. Okay, so in other words, this at least on the open disk, the map gamma that you find by this theorem actually is actually an immersion. Okay, so actually, and this really strongly uses that you're in codimension 1, because as we already saw in codimension 2, you can't have this possibly be true. So one remark, and I don't want to dwell too much on it. So there's an issue here which is. On the interior, we solve some nice problems, so we're really like real analytic. We're as nice as possible. But the question is the regularity at the boundary is a little less clear. So if we assume, as we do, that C is smooth, then you get that the map gamma actually extends to a smooth map to the boundary. And in general, if the boundary is to say CK, then you get a map that's CK. And if it's real analytic, then you get a map that's real analytic up to the boundary. The thing, though, is that even if the map is real analytic up to the boundary or smooth up to the boundary, it's not completely clear that, and this theorem doesn't guarantee that there aren't sort of branch points at the boundary, like that there's sort of the image itself might be singular at the boundary, even though the map is not. So you can adapt the Gulliver-Osserman proof to prove actually that there are no boundary branch points when the curve C is real analytic. But it's not known if that's, this is probably one of the biggest, and it's surprising given how classical the theory is that it's not known, but it's not known whether if you have C smooth, if you can still rule out a boundary branch point or not. So that's a very, to say that the field is old, but is also still there's still interesting questions. Okay, so then, the other thing I want to mention, and just before I sort of discuss the proof of this, we're going to we'll sketch a proof where we prove this by sort of the direct method. I'll try and outline the relevant steps. So the thing is that to show the map itself is smooth really is not, in a sense, it's going to boil down to a kind of PDE argument. We're not going to really use, we're going to use essentially, what I mean to say is we're going to use that we have a critical point of the which satisfies some elliptic equation. We're not going to use the minimization property. But this proof actually is very important about having that we are at a minimum. So the idea is that you could have higher index critical points, or even non-global minima, which in principle have branch points, but this is really using something about the variational problem, and somehow this is sort of a local. This will be a kind of a local. The regularity you get here in 2 is local, whereas this is sort of global. Right. So in fact, one can. We'll see after I sketch this. I'll present a kind of way of constructing lots of harmonic weakly conformal immersions, and we'll see that branching is pretty easy to construct in general. And so that means that it's not enough to just be a critical point. You really need to use the variational characterization of the plateau solution to get this. And then the final thing is, what about the regularity of the image, right? So this tells you at least the map is an immersion on the interior, so that we get that gamma is an immersion in codimension 1. But when is the image, say, actually a smooth curve? So when can you rule out self-intersection? So clearly you need some further conditions on the curve, because just take a knotted curve and you can't fill that in by something that doesn't self-intersect. So one condition, which is a number of different people, but so one consequence of a more general result of Meeks and Yao, which I won't state, but I'll just mention their result. So if C is a subset of the convex hull, the boundary of the convex hull of itself, so this is sometimes called being extremal, then this implies that the gamma is at least the gamma you get is an injection. So this actually tells you the image is smooth as a surface in R3. So like lots of there's a lot. I mean, it's easy to find an example. Like just take the unit sphere and just take a curve in the unit sphere, and so that's if you fill that in, the least area disk in this case is which is the plateau solution is embedded. Okay. Okay, so let me try and just sketch a proof of this fact. Okay, so we want to kind of we want to try and use. I mean, we want to prove that. I mean, this is the gamma we're trying to get is an area minimizer, so it makes sense to try and take some minimizing sequence and construct from that a limit, extract a limit, and sort of say that that should be the gamma we want, and then just argue that it has to be regular. Right. So the idea is to sort of introduce some class of space of guys, which should be maybe like gamma, that are just, say, smooth maps. Or, I mean, it might, in some sense, it's better to maybe weaken the regularity so that maybe they're locally Lipschitz, so something like the area makes sense, but it's a little bit better behaved under I mean, it's a bit more general, but let's just, for simplicity, assume it's smooth to Rn. And we're going to assume that the point is our class, which is that we're comparing, is that when we restrict to the boundary, that this is, let's call this gamma, this is supposed to be a parameterization of the curve C. So in general, this will be a little bit too big, so we want to restrict this a little bit to say this is what's called a monotone parameterization. So an example of a monotone parameterization would be if this was an injective map. But we need to allow a bit bigger of a space. So monotone just means the preimage of every point is a connected interval. So the intuition is, as you traverse the boundary of the disk, you're supposed to traverse essentially traverse the curve without going back. So that's the point. But you need to allow things to be a little bit weaker. And I mean, really, I mean, really, this smooth up to the boundary, we're not going to make everything work, we're not going to have it, it'll be C infinity on the interior and sort of continuous up to the boundary. So these are really going to be, we're not going to be able to control the sort of normal derivatives a priori. Okay, so this is our class, right? And the point is, in general, if we were in a manifold, we'd have to make sure this had something in it. But since we're in Rn, we can just use the fact that every curve is contractible to argue that there is something in here. This is non-empty. The other thing you have to convince yourself of in general, if you're treating very general curve C, but it's automatic in our case, is that there is some gamma naught inside of C so that the area of gamma naught is finite. Right, so in the classical theory that Douglas and Rado considered, they, for various reasons, wanted to think about continuous curve C. And then there's some issues about whether there's even a finite area disk that spans the curve. But that's not an issue for us. Okay, so if that's the case, then right, there's a well-defined notion of the minimum area, which is just the inf over gamma in C of the area of gamma. Right. So it turns out that for non-trivial C, this is bounded below by 0, which is, you should have to justify, but there's a number of different ways to see that. But let's just take that for granted. We'll see it in the, I guess in the end, we'll prove it, so we don't really need it. Okay, so we have this A min. And so the question is, can we just take a minimizing sequence of maps here and try and get them to converge to the gamma we want so that it has area A min? So in general, the idea is to take a minimizing sequence right, so take a gamma I in C so that the area of gamma I goes to the area min. Okay? But there's, of course, two problems. So the first thing, which I talked a lot about yesterday, was that we can reparameterize gamma and preserve this condition. But of course, after the reparameterization, we can make all kinds of crazy things happen. So, for example, we can make gamma I kind of converge to a constant map, which of course that means the limit is not even in our class C and has 0 area. And so, that's bad. Another bad thing, which we'll have to deal with as well, is the fact that even if somehow, even the images in some sense could be bad, right? So let's say we had our curve C as just a unit circle, so the least area disk turns out to just be filling it in with the flat disk. But the problem is that if we take little tentacles, right, and they can be pretty geometrically complicated, they can go everywhere. There can be lots of them. If you work it out, like the little tentacles add very little area to the disk, and everything's still a disk because you just push down with your finger and you haven't changed the topology. So the problem is that the area is not controlling the existence of these tentacles at all. So even if we tried to think of the image as a set, if we just took the limit set theoretically, we could get the whole space, even though the area was sort of going to this minimal area, which is supposed to be just the area of the flat disk. So, that's another issue we're going to have to deal with. And there's also an issue, one has to then see that sort of set theoretic convergence, even in this sort of, if you just think about the images and not the parameterization is not good enough, you need some way of kind of characterizing the fact that these guys are negligible. And of course, in the end, they're negligible because they have almost no area. So you have to kind of work, maybe not with this image, but somehow some measure supported on the image, where these things definitely are viewed as negligible. Anyway, right. So as we mentioned, right, our main idea is to not to think about maybe the area. At least that deals with this parameterization issue. So the idea is now to consider the energy minimizing. Okay, so there, you take a E min as then the inf of gamma in C of the energy of gamma, right? And so now this of course depends on the parameterization and not the image. So we fixed one of the problems. So then one has to check, but we sort of alluded to this, how to do this, at least for GD6. You have to check that the A min is equal to E min, right? Right, so remember, what this really boils down to is the fact that if you have a weakly conformal map, then the area and the energy of the map are the same. So for an immersion, you can use the uniformization theorem to sort of verify that. But in general, and that basically gives a proof here as well. But you should convince yourself of that. So the problem, though, is that the energy minimizers, in a sense, we sort of can't, it's not entirely, it'll take a bit of, it's not entirely clear that sort of these tentacles can't occur in the energy minimizing problem. So the reason for that, of course, is that, we don't have a Sobolev inequality in dimension 2, right? We can't control the C0 norm, which is what this distance is, in terms of the Dirichlet energy, right? We don't have a Sobolev. We just barely don't have it, but we don't have it. So we can't easily rule out tentacles. In fact, we should expect we can't rule them out at all, but. But the point is, what we can do is, the energy has nice behavior. We're really just looking at sort of the Dirichlet energy of a single of an n tuple of functions. So the idea is we do a sort of harmonic replacement. So we do a harmonic replacement. Right, so if gamma I is a minimizing sequence, right? So then the idea is we're going to we introduce a new map, which is gamma I tilde. So the point is gamma I tilde is supposed to, on the boundary of D, is equal to gamma I on the boundary of D. But now we assume that the Laplacian of gamma I tilde is equal to 0. So in other words, gamma I tilde are harmonic maps. So the key thing here is that they're not, we're not saying anything about their conformality properties, so their imaged are not minimal surfaces. We're just replacing the gamma I by gamma I tilde. And so here we use the fact that, so we use the kind of convexity of the Dirichlet energy. So you should convince yourself of this, but it's actually a fairly simple integration by parts in this Euclidean space. Convexity of Dirichlet energy is going to tell us, right, so the fact that the Dirichlet energy is convex when you fix the boundary means that there's only one critical point, which is the harmonic map. And that means that because it's convex, right, if you think of the energy, here's supposed to be the gamma I tilde, and then here's, say, gamma I. So we've decreased the Dirichlet energy because the energy is convex, and so the only critical point is there's only one critical point, which is the gamma I tilde. So that means that actually the gamma I tilde, right? So this implies the gamma I tilde are still minimizing. Okay. All right, so there's one final thing we have to deal with, right, which is, remember, the Dirichlet energy is conformally invariant. So if if phi is in this automorphism group of the disk, in general, the energy of phi is the same as the energy of of phi, right? So it would be gamma I tilde. Right. So, and the problem is this is not a compact group, right? I mean, we had these elements that were coming from, say, z goes to n times z, and that said that we could, in principle, take any gamma I tilde and compose it with one of these maps and converge somehow to a constant map, right? So we need to kill this guy, and this is somehow I mean, in the end, this is not so bad because we sort of know exactly what's going on in this automorphism group, which is that we're taking. I mean, how does this work on the boundary? It just takes 3 points to 3 other points. I mean, you should convince yourself, but this guy acts. This acts transitively on 3 points on the boundary of D, right? So the automorphisms of the unit disk extend to maps of the closed disk, and what they do is they take the boundary to the boundary, and you should convince yourself you can take any 3 points to any other 3 points. But once you take, I mean, there's a unique guy that takes the 3 points to the other 3 points. So to deal this, we actually we sort of mark 3 points, P1, P2, P3 on D, and 3 points P1 hat, P2 hat, P3 hat on C, and so then we just force, and we can always do this by applying one of these elements of the automorphism group. We have forced that gamma I tilde of Pj is equal to P hat j. Okay. So that kills the symmetry we had here. And I mean, we have to be a little careful, obviously. Right, we have to be a little careful because, we're not assuming this map is injective, right? But the point is, that means we have to be a little careful about the choices we make. But it's not such a big deal to make that work. Okay, so now we have the these gamma I tildes, and now they really have as much. I mean, they really converge to something, and they converge to something at least they can't converge to like a constant because of something like that. So then the point is, I mean, we have to use some theory, but right. So this is basically you think of this as sort of a PDE for. Yeah, and so then we solve the Dirichlet problem. So we fill it in with the harmonic extension. What? No. Remember, this is where I think. Remember that our class C is that what we have here is we're just saying that on the boundary there are certain parameterization of the curve. The curve is fixed, but this is a. Does that make sense? No. So see, we're fixing the curve. We're not fixing the parameterization. And then our class are all possible. Our class allows any parameterization of the curve that's monotonic. Does that make sense? So we don't. I mean, the idea is we're trying to find sort of the right parameterization of the boundary so that the harmonic extension is actually weakly conformal. I mean, that's what it all boils down to in the end. Does that make sense? Right. I mean. Right. I mean, the gamma I tildes don't necessarily agree on the boundary, but their images agree on the boundary. The images of the boundary agree. That's what the setup is. Okay. Okay. So then. And I mean, the point is now we have a sequence of harmonic functions where now we have harmonic functions where, but the point about the gamma I tildes is now we have a regularity theorem for them. So, I mean, in general, the energy can't control these sorts of tentacles, but when we take a harmonic function, then, I mean, we have good estimates, right? So the estimates on a harmonic function are going to say there shouldn't be these sorts of tentacles, at least on the interior, right? So we have sort of interior regularity for harmonic functions. Right, that is going to imply that the gamma I tilde converge uniformly, and this is important, on compact subsets of D to some gamma. Right, and this is going to be, this now takes the open disk to Rn is harmonic. Okay? But here, I mean, we're not quite done because we don't actually know what's going on at the boundary of this guy. So we don't even know if this is in our class, right? This is uniformly C infinite uniformly. So okay, so we need to be able to extend to the boundary, right? So that requires some additional work, right? So again, the issue would somehow be we had a minimizing sequence where here's the curve C, and here's sort of the image of gamma I tilde. So we could imagine that somehow there's some tentacle, and sort of in the limit that sort of the tentacles are approximating the boundary, and so in the limit somehow we have something like we've sort of gained some tentacle at the boundary, and we can't rule that out by the regularity theory because we can't control it all the way up to the boundary. Does that make sense? So the trick there, and this is something we do have to deal with, right? Right. So the idea here is we need to use this. This is where we use two facts. One is sort of related to this Meeks-Yau theorem, which I erased. So we need to. So the final step, and maybe I'll say it, and then the final step. I mean, not the penultimate step, if you will. Penultimate step is that we prove actually that the gamma I tilde converge. This is uniformly in some C0 sense on the whole of the closed disk to some gamma. Okay, so now this map is smooth. Right, so this is smooth on the interior, but say C0 on the boundary, in principle. And then once you have that, then you can do some other analysis to relate the regularity at the boundary to the regularity of C. But I don't want to get into that, right? Because then this implies then that gamma really is in our class C, and so then the final step is now we have that the area minimized. Well, right? We have A min, which is equal to E min. Is less than or equal to the area of gamma. Well, let me put it this way: A min is less than or equal to the area of gamma, right? But because gamma is in our class, and A min is the minimum of our area. But then this is less than or equal to the area of energy of gamma by just the area energy inequality. But then by construction, I mean, you have to use the sort of. I mean, this is something to check, but I mean that the convergence is such that the only thing that could happen to the energy is that it drops. So since we're taking a minimizing sequence, this means the energy of this guy is less than or equal to the E min, but as we already established, that's equal to A min. Right, so we have to have equality throughout, and so then the final thing that tells us is that we have to have equality here, and that means the map is weakly conformal, and then we're done. Okay? So then we're done. So then the question is, what's going on here? Why do we get this uniform convergence? And again, the geometric picture is why are we not getting these sort of tentacles kind of at the boundary in some sense? Okay, so Right, the point about that is that we have to, okay, so we have to pull out the tentacles at the boundary, and so then we have two ingredients. So there's two ingredients. So the first is the two ingredients. So let's deal with this penultimate step. Okay, so the first ingredient is fairly simple. So this is just a kind of convex hull property. So this is just the maximum principle for harmonic functions. Okay, so here the idea is that if we have if gamma of, say, the boundary of omega, so gamma is a harmonic map. If this is a subset of some convex set, this is convex, then this implies that actually the image of all of omega is a subset of the convex set. Okay. Right. So the idea is, right. I mean, remember the convex set is the intersection of all half spaces containing it. So if you just look at the sort of linear or the affine function defining the half space, this tells you that affine function has a sign on sort of the boundary of omega when you compose with gamma, and that, I mean, what that really means is that it's, I mean, the coordinate functions are really harmonic functions by definition of being a harmonic map. So that means you have a harmonic function on omega, who say has a sign on boundary omega, and so then this just tells you that it has a sign on the interior, which is just the maximum principle. So that means that if we can control sort of the boundary behavior of a harmonic map, then we kind of in C0, then we get some C0 control of the interior. So the second thing, which allows us to control the boundary behavior, is this so-called Courant-Lebesgue lemma. So this is closely related to the Sobolev embedding, or the failure of the Sobolev embedding. So the idea is, given this curve gamma, so let's just say gamma takes d to Rn as harmonic. Well, in this case, we don't even need, sorry, this is harmonic, but in this case, we don't even need, this is any map of sufficient regularity. Right, so if we consider the L of R to be the length of the boundary of dr centered at a point P, right? So here we have the unit disk. This is D0 inside of, which we think of inside of R2. So now we take any disk centered at any point P of radius R, okay? And so, sorry, LR is the length in Rn of the image of this space, okay? Right, so over here we don't, if we have a situation like this, we're just considering this arc, okay? But in general, this is, I mean, if you're entirely contained in the unit disk, we look at the whole image. But then, the point is to, the point of this is we get the following result. So then we get that the length of R is controlled by the energy of R in the following way. So if we integrate from 0 to infinity dr and put a squared here, then this is less than or equal to 4 pi times the energy of the map gamma. Yeah, that's it. And I mean, this is, for our purposes, this implies that if you take any two scales, A and B, that the minimum over A less than or equal to R less than or equal to B of the length of R squared, right, is less than or equal to 4 pi, the energy of gamma, divided by the natural log of B over A. Okay? And this is just like, if this wasn't true, if you didn't have this, notice this is just the minimum, right? We're not controlling the length on every radius. We're just controlling the minimum length. So there's some radius which just satisfies this. And of course, if this wasn't true, you would just have the reverse inequality everywhere, and then you would violate this inequality. Okay? And again, you should think about that. This is really about, I mean, if you just think about the map gamma into R, right, this is really just a result about, this is just the C0 norm in some sense. Or not, I mean, this is very close to the C0 norm. And so this is somehow related to the failure of the Sobolev embedding. So it's convenient to think about, I mean, just to have something in mind, think about like just gamma of x is equal to log x, right? So this is the usual counterexample to the Sobolev embedding, right? So this has finite Dirichlet energy, but it's not bounded, right? So you should think about taking a point. Think about pointing. Here's 0, and here's where the function is blowing up. So just think about taking a point like here and taking the radius r here. So right. So you can kind of see that if you take a very narrow band of radii around the singular point, then which corresponds to this guy, this ratio being giving you a very bad bound. This is supposed to tell you, why if you take a big bound, you get a better estimate. So I mean, just think about how this relates to this example. I think it also shows why you definitely need to take a range. But anyway, the way we use this to prove, let me just sketch how we use this to prove the boundary regularity, right, or the boundary convergence is. Right, so suppose we just have our closed disk and we fix this is a point P, and we look at the gamma I tilde, right? So we can look at the image of the boundary. So the image of the boundary is C, and we have this gamma I tilde of P, which maybe we can fix everything so it's mapping to one point. But obviously, this could move around, but let's just pretend it's mapping to one point for the influence of the drawing, for the point of view of the drawing, right? So the idea is if we take, right, by the lemma, if we take some radius of a ball centered at P, right, we know our maps all have a uniform energy bound. So if we, in a sense, if we pick right, if we're careful and we pick, if we pick, as R gets small, right? So let's say we take, A like, right, let's say we take A sort of roughly of the size square root of R, and B roughly of the size R, where these are both small. So this is roughly the log of R, where R is small, so that's a big number. So we're dividing a big number, a fixed number by a big number, so this is small. So this means that we can sort of take sequence of radii that should map to sort of small guys around here, right? So that the image is short. But then the point is, if we didn't have a good C0 control inside, like then there'd be these long, thin necks, and that would sort of violate the convex hull principle. It's a little more complicated, but of course, because somehow the tentacle could all be living inside of the neighborhood of the thing. But in some sense, from C0, that's okay. Like we're not claiming we're controlling. All we're claiming is we're controlling sort of. We could also, of course, have something like very complicated, like a tentacle like that. But the point is, it's in C0. It's close to the point P. Right, and so the key thing here is that we can control the length of one of the sort of arcs using this Courant-Lebesgue lemma, and then the convex hull property allows us to use that control to control the C0 norm of the parameterization on the inside. Okay, so that's obviously you have to make this a little more, do this more carefully to make it quite precise. Okay, so that's the idea. You see, we see that. We had to think about this. You definitely have to think about this conformal invariance in understanding this. Okay, so this gives us one way of finding lots of harmonic or minimal surfaces, right, by this sort of minimizing procedure. But they're all kind of compact. So we're actually going to now switch this in the last part, and this connects very closely with what we talked to, and see how we can give lots and lots of minimal surfaces in R3. In a sense, we can give all of them in terms of a complex analysis, which is sort of interesting. Okay, so now we're going to look at the most classical setting, in a sense. Okay, so we're going to look for, say, so in other words, some minimal immersions into R3. Okay, so this is supposed to be like the analog of looking at GD6 in R2, which of course, that's a totally trivial result. There's just a straight line. So interestingly, though, though unsurprisingly, it's not trivial once you go up a dimension. So just to convince you of that, right, some examples of these. So one say map you could take is just to take R2, which if we want to think of this as a Riemann surface is C. So we take xy to, okay, that is trivial because that's just a plane. That's a minimal surface. So you can check it's a minimal surface either by seeing that it's totally geodesic, and so its mean curvature is 0, or equivalently by seeing that in this parameterization, if we identify this with Z in the natural way, then this is a conformal and harmonic immersion. Okay? So less trivial is the following, which is we take R cross S1, which again, here we're going to think of this conformally as the punctured complex plane. So the cylinder is the same as the punctured complex plane, and that's going by T of theta gets mapped to cos HT, cosine theta, cos HT sine theta T. And this is more interesting. So this is a surface of revolution that sort of is what you obtain from a catenary. So this is the catenoid. And this was discovered by Euler in the 18th century. And sort of geometrically, it looks like two planes at infinity, but you have this neck connecting them. Okay, so this is a classic surface. And it shows why it's fair to look at these guys. And notice, this is an embedded surface, so this really is smooth in every sense that we have. And then the final guy is the, say, the helicoid, which again is very closely related. So again, we think of this as C. And so then we take x and y to okay, and so this one, if you've seen it, which you may or may not have, this kind of looks like DNA, like it's a kind of double helix. So that's also minimal. And again, you can just compute this. For example, just compute with the standard complex structures that you would expect from this, that these maps really are harmonic and conformal. So the point is we can actually, and this is sort of remarkable, we can actually find lots and lots of other minimal surfaces. And in fact, this is one of the few kind of, I would say, nonlinear elliptic equations where you really are pretty sure you can find all of them, and you don't have to use sort of more complicated techniques. So just to show you that, this is not always so easy, right? So there's another example which is due to Costa, and this was discovered in the 80s. And so there's various other of these sort of complete minimal surfaces that were discovered throughout the history of mathematics, right? So this one starts in the 18th century with Euler. So interestingly, we already get to the 1980s and we find new ones. So it's definitely there's something there. And so what he did is he found a surface that sort of looks like a catenoid on one end and looks like a catenoid on the other end. And in between, it has kind of a plane. But then how do you put this all together? So you put it together, you need some kind of handle, it turns out. And actually, that's a theorem. All right, I don't know how clear. All right, I can't draw, but roughly what you get up is it's topologically, it's a torus with -3 points. And the point is each point corresponds to a direction like going to infinity, and you go to infinity either like half a catenoid, or a plane. So the hard thing about this is that it's embedded. That was not obvious. And in fact, people were kind of surprised. Once people found this, people realized there's lots of these and constructed a whole bunch of them. But it was actually very surprising when this was discovered because people were sort of not, in a sense, not expecting it. So I think I have about 10 minutes, so let me just very briefly try and explain how you might get this using complex analysis. Okay, so the first observation, which let me just do this for disks, right? Is let's say we have gamma taking the unit disk to R. Well, let's say actually we can do this in Rn. We'll see why R3 is special. So this being a weakly conformal plus harmonic. If we actually think about D now as a Riemann surface, right? Remember we have dx and dy, but we could also just take dz and dz bar of this. So we're going to recast this in terms of dz and dz bar. So the harmonic, right? That's the same as saying d dz of d dz bar of gamma is 0, right? Where here we're just applying this to each component individually, okay? So in other words, what that means is that if we think of the map dz of gamma as a map from the unit disk to Cn, right? Remember here d dz is 1/2 d dx minus I d dy, right? Then we can see that this gamma is harmonic if and only if d gamma dz is holomorphic. Okay, so the harmonic part, which is the linear part, we can kind of understand in terms of this complex picture, which is nice. But what about this conformality condition? So the idea is if we extend the inner product on Rn to Cn, so that, for example, such that, for example, Z inner product W is complex linear in both factors. So it's not a Hermitian inner product, right? We're not saying that it's complex antilinear in one factor. It's complex linear in both factors. So just to be pedantic, like x plus iy, z plus iw is supposed to be equal to xz minus yw just in dimension 2 plus dimension 1, but this makes sense component-wise, plus I xw plus yz. Okay? So if you work that out, then what you actually should convince yourself of is that the weak conformality basically means, just looking at what this is just complex multiplication, right? This is just a multiplication of the two complex numbers. So the point is the weakly conformal corresponds to the following nonlinear condition, which is that the derivative of f dz, the inner product of that in this complex linear way, is equal to 0. Okay? But as I said, this is really, this in a sense means that Right, this is not Hermitian. I mean, this is sort of interesting if you think about it. So this means that right. So this means that essentially d gamma. You should be gamma. Sorry. That d gamma dz is a subset of the following quadric in Cn, which is w1 squared plus. Okay. Okay. So now this is all in a disk, but we can think about this actually on a Riemann surface. So if we have the same thing where now we have gamma taking a Riemann surface to Rn. Right, so instead of looking at the ddz, we look at this del of gamma. Right, so this is now a n-tuple of holomorphic. Right, we work out the local thing tells us that this is an n-tuple of holomorphic 1,0 forms. Okay, and we want to kind of interpret this weakly conformal. So that means that if we take this tensor product, del gamma tensor del gamma, which is sort of an n-tuple of elements of sections of the 1,0 tangents of complexified tensor space tensor of X. Okay, then the point is these guys also satisfy a kind of quadric if you choose a local coordinate, right? But my point about doing this is that if we change local coordinates, right, we're going to change the gamma we get by multiplying by a constant. So the observation you're supposed to take away from this, which sometimes is not made, but right, if we work in local coordinates and we use the fact that everything's holomorphic, okay, so working, the way to think about what this means, and you can just think about this in holomorphic coordinates, that really we get a natural map. Let's call it like hat partial gamma that takes X to Cpn minus 1. Okay. The idea is, for example, I mean, the point is if we expand this in local coordinates, we map into Cn. But if we change coordinates, we get a different map into Cn. At least change holomorphic coordinates. But if we think of it as a map into Cpn minus 1, we get the same map, right? So that's the observation, is that this is a well-defined map into Cpn minus 1, at least away from branch points. But then you convince yourself that actually at branch points, because everything's holomorphic, you can extend the map. So this map extends. And then the question is, well, what is this? So and this is a holomorphic map by the holomorphicity of the map of the fact that the one forms are holomorphic. But then the question is, what happens to this quadric on Cn? Well, this is a homogeneous polynomial, right? So this is supposed to be equal to 0. Right. This is equal to 0. So this actually means that there's the image lies in a quadric Q hat, which is given by x1 squared plus xn squared. Okay, Zn w. Say. Okay. So now we get to see why is dimension 3 special. Okay. So in dimension 3, we have a map from X into CP2 that lies in this quadric Q. But what's a natural parameterization of a quadric in CP2? Right. So there's this Veronese embedding that says that CP1 is equivalent to this quadric in CP2, and so what happens is in dimension n equal 3, we actually can sort of factor everything through this Veronese embedding. So we take a modified Veronese embedding. So we take a modified. So we consider the map from CP1 to CP2 given by sending Z0, Z1 to, let me just get this right. I never remember it. 1/2 Z0 squared minus Z1 squared I over 2 Z0 squared plus Z1 squared Z0, Z1. And so the point is, if we want to associate to this del bar, I mean, the idea is then to use this, using this, we associate sort of guys, omega 1, 0, and omega 1, which are somehow they're somehow what you might call half-zero forms. I might have chalk. So they're holomorphic, and they're holomorphic. So the idea is, if you plug this into this kind of embedding, you're supposed to get the del of omega. But the observation is that, I mean, we don't usually think about these. So the observation is if we take omega 0, omega 1, which is a 1-0, holomorphic 1-0 form, then this is supposed to be equal to, this is basically del of gamma 3, so it's the third coordinate, if you believe this embedding. So in other words, it's equal to, if you like, the gamma pullback of dx3 plus I dx3. Okay, if you work that out. But what's sort of remarkable and I think a little mysterious, right? So that's one piece of information, this holomorphic 1 form. But the other piece of information to determine this is if you take their quotient. So if you take omega 1 over omega 0, this turns out to be a meromorphic function. Meromorphic. And what's sort of remarkable is this actually turns out to be the Gauss map, so the unit normal map, where you identify the Riemann sphere with the unit sphere in R3. So it turns out to be. So the idea is then you can go from your gamma and you can construct your Riemann surface, which is you're given in some sense with your gamma. Then you get this one form eta, which is omega 0, omega 1, and then you get this, which is the height differential, and then you get this meromorphic function g, which is eta 1 divided by eta 0. This turns out to be the Gauss map, which is not obvious. And then the point is, if you compute this del of gamma, then you have a formula exactly by this embedding. So this is 1/2. If you work it out, it's using this identification. This is the standard way it's written. It's 1/2 g inverse minus g. Sorry. Yeah, 1/2 this guy, I over 2 g inverse plus g, and then 1, all of this times eta. So this is so the point is you can then recover the gamma by integrating this guy. But if you work things out, you actually can see that if you just give in this data, then you can construct this del gamma from this representation. And if you integrate it, that gives you a weakly conformal harmonic immersion, a weakly conformal harmonic map. In other words, it gives you a parameterization of a minimal surface. And so this gives you an ability to construct pretty much every minimal surface by just this complex analytic data. So the only thing you need to be sure is if I give you a data, why does it give me a good map? Well, the problem is I'm trying to integrate something, so I need to make sure that when I integrate around a homologically non-trivial loop, I don't care about the imaginary part of this when I take the integral, because that I don't see when I try and go back to the real setting. But I want to make sure that the real part of any of these period maps are 0, so that I get a well-defined map on X. The other thing is, of course, you might also want to, as I said, make the map embedded or an immersion. And so you need to work out how these various quantities relate to the G and the eta. So being an immersion is just a local thing, so you can just work it out in terms of local behavior of G and eta. But being embedded is a global thing, so it's a bit trickier. But anyway, I'm out of time. So what you should do is just play around with various G's and etas and see what kind of surfaces you can get. But I'll stop here.